Hey everybody, welcome to my intermediate Milestone 2 presentation for EduTech CS6460. My name is Benjamin Ostrower, and my topic is on detecting AI written essays. So to start off, the motivation, why is this important? Why is this a problem that we should try to solve? Well, basically, with the advent of large language models and ChatGPT and the like, the ability to generate very coherent and human-sounding text is a capability that can now reach the masses. And this has effects on just about all aspects of society. For instance, someone could now write fake news articles or tweets that kind of disseminate misinformation. Somebody could be using this to write fake essays to promote a fake product. The list is really endless, but for the education sphere, the most immediate use, or malicious use at least, would be to use these tools to allow students to basically cheat their assignments and have sort of this indefatigable ghostwriter at their disposal. And obviously this is not in the institution's best interest. They need to ensure that students are learning something. These tools are very competent. ChatGPT was just able to pass an MBA exam given by Wharton. And because of how good these tools are and how ubiquitous they are, students are already using them to cheat, as referenced by this Daily Mail article where they spoke to several administrators of several different school districts that believe that half of their schools are already using ChatGPT to cheat. The response has been from many municipalities to just outright ban ChatGPT, like the LA County School System, Seattle Public Schools, etc. They all say that there's no good ways to detect large language model output. And these tools can challenge the future of higher education. They make it difficult to enforce the effects of this plagiarism because there's no good ways to detect it. And so because of this, schools are kind of at a crossroad of how to deal with it. Do they just revert back to pencil and paper, in which case that doesn't totally stop people because they could just copy it straight from a screen? Do institutions just integrate it into the curriculum, but then how real world ready are their graduates for an environment that, say, isn't allowed to use it? So institutions are kind of at a crisis with how to deal with this, but if they don't even have the option to know whether someone is using this or not, it makes it all the more difficult to pick the correct option for them. So detecting generated text from machines isn't a new topic. It's been around for a while. The prior work on this has centered around several different approaches, the foremost being analyzing the text on a token level. So GLTR and DetectGPT are some of the more recent, often cited works on how to do this. They work on analyzing the text on a token level, and they do this by measuring the entropy and statistical likelihood of token choices. And you can think of entropy as information gain. So to use a brief example, if I were to ask you to predict how many people are going to come into the office tomorrow, you would get a lot more information to get to the right prediction if I told you tomorrow was a Saturday than if I told you it was going to be sunny tomorrow. And on the statistical likelihood of token choices front, basically what they do is they mask a sentence. So take, for instance, the man walked through the blank. LLMs will be able to create a list of likely words to fill in for that blank. What these methods have done is to sort of chop up the whole block of text into these mass sentences and then analyze, okay, the real word choice and then what likely choices a large language model would have used for that. And then they run statistical hypothesis testing to see how likely it is that this whole work was written by a machine. Coherence measures are another way. Zhang, in his neural deepfake detection of text, creates a two-pronged approach using factual coherence and next sentence prediction. For his factual coherence, what he'll do is he'll embed the document for the pronouns. So, for instance, if an essay was written about, Jupiter and astronomy and used it would pierce out the pronouns like Jupiter and Saturn and all that, embed them in a embedding measure called Wikipedia2vec, which basically is able to sort of cluster semantically similar pronouns. So obviously if like a essay was talking about Jupiter and Saturn and Mars, and then in the next paragraph, it started to talk about Burger King and McDonald's, you would be able to see that Jupiter and Saturn and Mars are all kind of clustered together in a more similar area as opposed to Burger King and McDonald's. And then the next sentence prediction factor basically works. It's very similar to the token choice, but this is on a sentence level. And what it'll do is it'll feed a sentence in, use that, feed it into a decoder network, predict a sentence off that, and then measure the similarity of the actual sentence to the predicted sentence. Another method uses abstractive summaries. I can't pronounce the name, but in his paper, Neural Abstractive Text Summarization, he will pass abstractive summaries created from fake news articles to then detect whether that was written by a machine or not. And then finally, in Ludwig's paper, Automated Essay Scoring Using Transformers, he creates a very simple method where he basically just embeds the whole essay into a lower dimension, feeds it through a transformer, and outputs it into a automated scoring. So my plan is to effectively combine all these approaches. I intend to craft a neural network to encompass all of these into a binary classification model, then compare it against a baseline method, such as an LSTM combined with a convolutional neural network. You can kind of see at the bottom the very high-level architecture where the essays and summaries are obviously still in a textual format, so they will have to be embedded into a lower dimension, into a BERT architecture. Concatenate those two outputs, and then combine those with the token counts and the next sentence prediction probability scores into a multi-layer perceptron, and then that will output a probability score, which we can then run your classic classification metrics to analyze the performance of the model. So in my previous deliverable, so in my work to date so far, previously I had to scrape all these essays together because I was unable to find a large data set of usable essays across a wide range of fields. I had to whittle this down to about 1,300 due to computational constraints for text generation. I ended up using the Falcon 7B Instruct LLM by using the LangChain module and feeding it the prompt that you are a student, please write a blank word essay on blank, feeding it the title of the essay that I scraped and the nearest rounded to 100 word length of the essay. And then I was able to calculate the number of top 10 word samples for both human and AI written text. Due to computational constraints, I couldn't do this for every word, so I had to start at the 30th word and then do every 5th word. So some interesting finds. The inference for text generation, even on these relatively smaller models, still takes a long time. And the human and AI written number of top 10 tokens in an essay actually isn't too dissimilar. You can actually see that the AI number of top 10 tokens has a larger range of values to take on. And I mean, partially this is due to the fact that the LLM used to use for the top 10 list is different than the one that was actually used to generate the text. So in my most recent week, I was able to create extractive summaries for both human and machine written essays, and then obtain next sentence prediction probabilities for human and machine written data sets. So to do this, for the next sentence prediction module, Hugging Face provides this very nice pipeline where you can feed in a sentence and the actual sentence, and it will create a sentence based off of the BERT model, and automatically calculate the probability that that true sentence was written by the BERT model. Most of these end up being 99% no. So you can see for the human written sentence pairs, out of the 28,000 pairs tested, only about 1,000 had a probability lower than 50%, basically saying that this was written by a BERT. And comparatively, that out of the 1,800, only about 100 for the machine-written essays had a probability lower than 50%. So you can kind of see that it's a little counterintuitive, to be honest with you. But the machine next sentence prediction definitely has a lot less values out of that 99 percentile range. Moving on to the extractive summaries portion. Basically, the length of these summaries are very similar. You can see that the difference between an average a summary written on a human essay and summary written on an AI essay is less than 1/10 of a word. However, even though the AI written summaries are slightly longer, the human written essay summaries actually tend to have slightly more unique words in them. So again, these are all very similar. You can see by the box plots, the averages, the percentile ranges are very similar. It's just the machine will typically tend to have a little more outlier values to it. So for my final steps to deliver, I just need to develop the transformer network and a baseline network, that LSTM CNN network, to just have sort of a baseline method to compare to. I need to train and test these networks on my data set. I intend to hold out about 20% of the data set across all different essay topics to leave out as like a holdout set so that I can test the performance of these networks on unseen data. And then obviously report the results and see how they did using basic classification metrics such as accuracy and precision. So it's, for detecting AI written text, being able to get those false positives down will be very helpful. And that's my presentation. Thank you.